let us now discuss about ions or radicals. Okay. First of all, what are ions? You know, ion is something which carries either positive charge or a negative charge. Okay. And you know, it behaves as a single unit. Now, let me also tell you that the ions which carry positive charge are called cations. Okay. These are also called basic radicals. Ions that carry a positive charge are, of course, called cations or basic radicals. Now, those which carry negative charge are called anions or acidic radicals. Right. Now, how are these cations and anions formed? Let me just give you some examples. You know, when an atom loses an electron, atom loses one or more electrons. Cations are formed. Similarly, when atoms gain one or more electrons, anions are formed. See, we are actually heading towards writing the formulae of chemical compounds. I gave you information of how to write electronic configurations yesterday. And now we are going to form cations and anions, which in fact combine according to a method called Criss method. To give us the formulae of chemical compounds. Let me just give you one example each first. Now, let us take sodium. You all know that the atomic number of sodium is 11. Its electronic configuration can of course be given as neon 3s1, isn't it? Now, when sodium loses one electron, I mean this one electron, when lost by sodium atom, you get Na plus. Yes, because it has lost one electron. Now check out the number of protons and electrons in both the things. See, in sodium, you know the atomic number of sodium is 11. So the number of protons is 11. Even the number of electrons is also 11. If you want, I can also give you this way. Because it is a sodium 1123, the number of neutrons can of course be given as 23 minus 11. Isn't it? A minus Z is the number of neutrons. Check out the number of protons, electrons, and neutrons. Number of protons is equal to atomic number. That is equal to 11. The number of electrons is also equal to 11 because it is a neutral one carrying no charge at all. then the number of neutrons is of course 12. It is nothing but A minus a Z, right? Now coming to Na plus, if you consider this, see there is no change in the number of protons, remains the same, but one electron is lost. So only 10 electrons are there now. Coming to the number of neutrons also, there is of course no change. It is always A minus a Z. So this is again 12 only. So only change that has occurred during this is, you got a decrease in the number of electrons by 1 unit. Because sodium atom has lost 1 electron, you got Na plus, sodium ion. Okay, of course, we'll take one more example later, but let me now give something about the anion. Let us consider chlorine. Okay, now in this case, you can take, of course, 1735, even 1737. You got two isotopes. In case of chlorine, coming to chlorine, the atomic number is 17. How do you write the electronic configuration? It is written as neon 3s2 3p5, isn't it? Now, when chlorine gains an electron, only one electron, you'll get Cl minus, chloride ion is formed carrying a negative charge, nothing but an anion. Look at the number of protons, electrons, and neutrons in this. Coming to the number of protons, it is equal to atomic number. Coming to the number of electrons, equal to atomic number again. Number of neutrons, A minus Z, 35 minus 17. Now coming to this, number of protons, the same. Number of electrons, it has gained 1 electron. So is the difference. There were 17 earlier, now 18. Coming to the number of neutrons, no change at all, 18. So this is all about how ions are formed. Of course, we'll give you some more clarity on how the ions are formed, but for now, I think this is clear. Sodium is of course a metal. Metals generally have tendency to lose electrons. Metals lose electrons and form cations. Non-metals generally have tendency to gain electrons. Of course, there are some other things which, in fact, decide whether something gains electrons or loses electrons. But for now, let me just tell you that being a non-metal, it will have great tendency to accept an electron, and you got Cl minus here. Now, let me take one more example to give much more clarity. Again, an example for cation. And this time it is going to be little bit heavier. Let me take magnesium. Atomic number of magnesium is 12. Coming to the electronic configuration, come on, 1s2, 2s2, 2p6, 3s2, right? Now look at this. Every single atom tries to acquire noble gas configuration. This is the extra information that I wanted to give. But why? What is noble gas configuration? You all know that The noble gas configuration is NS2 as in case of helium, or NH2NP6 as in case of neon, argon, krypton, xenon, and radon. This, of course, I mean possessing 2 electrons in the valence shell is called doublet or duplet configuration. Now this, I mean possessing 18 electrons in the valence shell of an atom is called octet configuration. Now generally, any atom tries to acquire these configurations. It is because with these configurations, the noble gases are very much stable. Very much stable in the sense, they don't generally participate in the reaction. They are already stable. So there is no point in noble gases or the zero group elements participating in the reaction because they're already stable. Generally, elements, participate in chemical reactions in order to acquire stability. I told you. Now, in case of magnesium, if you observe, this configuration is of neon, right? Then coming to the remaining configuration, you got 3s2 extra. I mean, there are 2 electrons in the 3s sublevel of magnesium. If it can, if it wants to get stability, either it has to lose these 2 electrons so that now it will have the configuration of neon, or it has to gain 6 more electrons so that now it can acquire the configuration of argon. So this is very interesting. I hope it is very clear that losing 2 electrons is of course easy than gaining 6 electrons, because who is going to give you 6 electrons? It is very difficult to gain 6 electrons. It is very easy to lose 2 electrons. So being a metal, magnesium will always try to lose electrons. So it loses 2 electrons, and it forms Mg+2 ion, a cation. Now this Mg+2, which has got the configuration of neon, is of course stable because it has acquired the configuration of neon, which is a noble gas. Noble gases are stable because of their configuration. Because of their NS2 or NS2NP6 configurations, they are considered to be stable or inert towards chemical reaction. They don't participate in the reactions, so they are considered to be stable. Remaining all atoms, every single atom other than the atoms of the noble gases, try to acquire these 2 configurations. NS2, duplet or doublet, or the NH2NP6 configuration, otherwise called octet configuration. Let me give you one more example. For anion, let us consider oxygen. In case of oxygen, atomic number is 8. Coming to the electronic configuration, 1s2, 2s2, 2p4. Okay. Now coming to this configuration, see, 1s2 is the configuration of helium. Nothing but the duplet or doublet configuration. In order to acquire this configuration, it has to lose these 6 electrons. This is possibility number 1. Now coming to the second possibility, it has already got 6 electrons in this shell, the second shell or the valence shell. Let me just tell you what a valence shell is. For example, in this last shell is called valence shell or ultimate shell. The last one represented by N. Now coming to these two, 2s and 2p, I mean the second shell is said to be penultimate shell. We call it n-1. And finally, penultimate is last but one, isn't it? Then coming to this 1s, it is called anti-penultimate shell. Nothing but n-2. Ultimate or valence, n. Last but one is penultimate. The next, the next one or the one that is before penultimate is called anti-penultimate shell. Right? So that is how you can see. Other than the valence shell, remaining all are of course called core, and the electrons are called core electrons. Now these electrons are called valence electrons. I am giving you much more clarity. Valence shell, valence electron. Other than the valence shell is said to be core, and the electrons present in it are called core electrons. Now remember, in the valence shell, I mean the N shell, if you have this particular configuration, then that is considered to be a stable one. Now let us check whether our oxygen can get this configuration by losing all 6 electrons, or because it has anyway got 6 electrons in the valence shell, will it try to acquire 2 more electrons? Which one is easy? Losing 6 electrons or gaining 2 electrons? Obviously, gaining 2 electrons or losing 6 electrons. Which one is easy? Obviously, gaining 2 electrons is easy. Therefore, it tries to gain 2 electrons. Come on. Oxygen gains 2 electrons and finally forms 2 minus. Oxide ion is what is formed when oxygen atom gains 2 electrons, and now it has become anion. Now check out the configuration of oxide ion. Now it has actually acquired the configuration of neon, same as this magnesium ion, which has acquired the configuration of neon. Nothing but NS2NP6 configuration. So remember, any atom tends to acquire stability either by getting doublet or duplet configuration. That is possible, of course, only in case of hydrogen, lithium, even beryllium also, because lithium forms Li plus, hydrogen forms H minus. H minus is 1 plus 1, 2 electrons. Li plus, lithium has 3 electrons. When it loses 1 electron, it will be 3 minus 1, 2 electrons. Then coming to beryllium, 4 electrons are already there. If it, of course, loses 2 electrons, then you get beryllium plus 2. 4 minus 2 is 2 electrons. Yes, that is how they acquire doublet or duplet configuration. most of the other things, try to acquire octet configuration. I hope this is clear. So now this is what I am going to give. I am going to give you the list of radicals, list of ions. Come on. Now, before going for the list of ions and crisscross method, let me give you the types of ions. Okay. You know, there are two different types of ions. One is a simple ion. The simple ions are those which contain one or more atoms of the same element. Now you got just the atoms of sodium element, only one atom of the sodium element, of course carrying a positive charge, Cl minus, Mg plus 2, O minus 2. If you want, I can give some more like K plus. You can also go for Ca plus 2. You can also go for S minus 2. You can also go for Al plus 3. You can also go for N minus 3. Check out the things. You know, in Na plus, sodium contains 11 electrons. Now, 1 electron is lost. It has got 10 electrons. Nothing but it has acquired the configuration of neon. Coming to Cl minus, chlorine, of course, contains 17 electrons. Gained 1 electron. That's it. Acquired the configuration of argon. Isn't it? 10 electrons is nothing but possessing the configuration of neon. 18 electrons is nothing but possessing the configuration of argon. Coming to Mg plus 2, come on. Has already got 12 electrons. Now 2 electrons have been lost. So contains 10 electrons. Then coming to oxide. Yes, of course. 8 plus 2. Right. Same. Coming to K plus. Potassium has, of course, 19 electrons. 1 electron is lost. So has 18 electrons. Coming to calcium ion. Calcium contains 20 electrons. Minus 2. You got 18 electrons. Coming to S minus 2. Sulfur contains 16 electrons. Now, you know, it has gained. Minus refers to gaining. Plus refers to loss. 16 plus 2, 18 electrons. Again, acquired the configuration of argon. Coming to aluminium, contains 13 electrons. Now it has lost 3 electrons. So, acquired the configuration of neon. Coming to nitride, N minus 3. Nitrogen as such contains 7 electrons. Then, you know, it has gained 3 electrons. So, a total of 10 electrons. Again, the configuration of neon. Isn't it? So, these are all simple ions consisting of one or more atoms of the same element, only one element. Right. Now, let us go for the second type. It's called compound ion. What do you mean by a compound ion? Quite opposite to the simple ion. These compound ions, you know, they consist of one or more atoms. No, not one, of course, 2 or more atoms of different elements. Consist of two or more atoms of different SOIs compound. Different elements. See, I can give you examples like, for example, sulfate ion, sulfate ion. Say, for example, phosphate ion. See this. Here you got sulfur and oxygen. Atoms of two different elements. In this case, you got phosphorus and oxygen. Right? Atoms of two different elements. For example, you can say permanganate. You got the atoms of two different elements, manganese and of course oxygen. You can also take this. It is called bicarbonate ion. It has actually got atoms of three different elements, hydrogen, carbon, and oxygen. Hope now you have come to know why we have discussed electronic configuration in detail yesterday. So these are some of the compound ions consisting of two or more atoms of different elements. Okay. Of course, there is a very big list. Of course, we have to go for all those things, but for now, I've just given you these things. Now, I think you actually got one doubt in the meanwhile. Why is the positive charge when an atom loses an electron? Let us check that, taking the example. See, when sodium, let us suppose 1s2, 2s2, 2p6, 3s1, loses an electron. Of course, we all know that we get Na plus, and the configuration is going to be 1s2, 2s2, 2p6. Isn't this one electron is of course lost, and you got the configuration of neon. Then why is this positive charge? Check out. Of course, this I already told you, but let me give it once again clearly. How many protons are there in this? 11. How many electrons are there in this? 11. Of course, number of neutrons is now immaterial. Let us go for the number of protons in this also. You will have the same number of protons. Only thing is, one electron is lost. So now the number of electrons is 10. See, 10 protons and 10 electrons. Of course, cancel out their charges. What is the extra charge that we have? One extra positive charge is what we have, isn't it? So that is the reason why you got your positive charge here. Protons are positively charged. Electrons are negatively charged. You got 11 protons and just 10 electrons. I mean, you got one extra positive charge as compared to the negative charges. So is the reason why you got Na plus. Right. Now coming to the negative charge thing. Let us take the same old example. Chlorine 1s2, 2s2, 2p6, 3s2, 3p5. Now Let me also recall your memory. Valence shell, penultimate shell, anti-penultimate shell. Now when this chlorine gains an electron, we get Cl minus, right? See how many protons and electrons are there in this. Number of protons is 17. Even the number of electrons is also 17 here. And coming to Cl minus, what do you get? 1s2, 2s2, 2p6, 3s2, 3p6. Because it has gained an electron. Now, look at this. It has acquired the configuration of argon. Check out the number of protons and electrons. Number of protons is the same, no change. Whereas the number of electrons is, of course, 18. You can clearly see that there is one extra negative charge. That is what has actually come here. Got it? I hope you came to know how important writing the electronic configurations. If you can write the electronic configurations, you will come to know the number of electrons that are to be lost, the number of electrons that are to be gained in order to acquire a noble gas configuration, in order to acquire a stable configuration. That is how you can form the ions. That is the reason why we have gone for orbits, suborbits, orbitals, and electrons concept. After that, the electronic configuration concept. So that is how we are slowly building up the chemistry of elements. Okay, now let me now go for something very interesting before going for Criss-cross method. Now this is of course called valency of elements. Simply speaking, valency is the combining capacity of elements. I mean the capacity of an element to combine with the other element. How many atoms of one element combine with how many atoms of another element? This is what I call valence. Right. Now, you know, valency of elements is determined taking three elements as reference. What are the three elements and why only those three elements? Let me tell you answer to these questions. You know the three elements are hydrogen, chlorine, and oxygen. And answer to my second question is why only these three? You know, because only these three are the elements which combine with most of the elements that we come across in the periodic table. Right. Now let us see in detail about what is valency with respect to hydrogen. See, before giving you the definition, let me take one example. After that, I'll give you the definition thing. Now, what is the valency of chlorine with respect to hydrogen? You can clearly see that. You know, one atom of chlorine is combining with just one atom of hydrogen. I mean the number of hydrogen atoms with which one atom of chlorine is combining is just one. Let us take one more example to make it little bit more clear. Now look at this. One atom of oxygen. Remember, you should always say valency of just a single atom. Now here, one atom of your oxygen is combining with two atoms of hydrogen. So what is the valency of your oxygen with respect to hydrogen? Of course, 2. Hope you are following. Let me give you one more example. Now in this case, you know, one atom of nitrogen is combining with 3 atoms of hydrogen. So the valency of, the combining capacity of nitrogen with respect to hydrogen is 3, because one atom of nitrogen is combining with 3 atoms of oxygen. One more. See here, one atom of carbon is combining with 4 atoms of hydrogen. So the valency of carbon with respect to hydrogen is 4. Hope you got my point. So here we are just giving the number of atoms of an element combining with hydrogen. The number of hydrogen atoms. In this case, in the first case, if you can see, one chlorine is combining with just one hydrogen. So the valency is just 1. In the second case, one oxygen is combining with 2 hydrogens, 1 with 2. So valency of oxygen is 2 with respect to hydrogen. In the third case, one nitrogen is combining with 3 hydrogen atoms. So the valency of nitrogen, of one nitrogen with respect to hydrogen is 3. You should always say valency of just one element. Coming to this, one carbon is combining with 4 hydrogen atoms. I think now I can define the things. Define valency with respect to hydrogen. Simply the number of hydrogen atoms with which one atom of an element combines. Once again, the number of hydrogen atoms with which only one atom of the other element is combining. One atom of chlorine is combining with one atom of hydrogen. So is the valency of chlorine became 1. Is that okay? So this is valency with respect to hydrogen. Let us go for valency with respect to chlorine, which is almost the same, similar. Coming to this, valency with respect to chlorine. Let me give you examples first, then of course the definition part. Come on. You know, in this, now here the reference is chlorine. One atom of sodium is combining with just one atom of chlorine. So the number of chlorine atoms with which one atom of our sodium element is combining is just 1. So the valency of sodium with respect to chlorine is 1. because one sodium is combining with one chlorine. Similarly, look at this. What is the valency of magnesium here? Clearly visible, 2. It is because one atom of magnesium is combining with 2 atoms of chlorine. Now look at this. Valency of aluminium with respect to chlorine is 3, because one atom of aluminium is combining with 3 atoms of chlorine, clearly visible. Go for CCl4. Valency of carbon with respect to chlorine is 4. Valency of phosphorus with respect to chlorine is 5. Okay. This is how we can just go on giving valency with respect to chlorine. I think it is again clear that it is the number of chlorine atoms. That's it. Just the number of chlorine atoms with which one atom of an element combines. Number of chlorine atoms. 1 here, 2 here, 3 here, 4 here, 5 here. Of course, they are the valence with which only one atom of the other element is combining. Hope this is clear. Now going for the third one, you need to be a little bit cautious. Valency with respect to oxygen. This is going to be interesting, bit complex also. You need to be more careful. It's not just equal to the number of atoms, but double the number of oxygen atoms, not equal to the number of atoms as we have seen in case of valency with respect to hydrogen and valency with respect to chlorine. Let me give you some clarity taking this example. Look at this. You know, 2 sodium atoms are combining with 1 oxygen atom, right? But we always say valency of just 1 atom. So 1 sodium atom combines with how many? Half. Make it half. So 1 sodium atom combines with half oxygen atom. So as such, if you say the answer, valency of sodium has to be half. If it were to be the same as the previous examples, previous definition. But here, it is not that. We have to consider double to this. What is double to half? Double to this is 1. So the valency of sodium with respect to oxygen is 1. Check out this. 2 sodium atoms are combining with 1 oxygen. But you all know that we never take for 2 atoms, we always take for 1 atom. We always give the valency of just 1 atom. Now see that 1 atom is combining with half oxygen. If the definition were to be the same as the previous 2, then the answer would have been half. But no, the definition here is not exactly equal to the number of atoms. It is double the number of atoms with which, double the number of oxygen atoms with which 1 atom of an element is combining. Let us take one more example to make it much more clear. Come on. Coming to this, you can clearly see that one atom of a magnesium is combining with one atom of oxygen. Of course, as per the definition, we have to take one. We have, of course, taken one. But when one magnesium atom is combining with one oxygen atom, you know, as per the definition, we have to take double to this. What is double to this? Of course, 2. So the valency of magnesium with respect to oxygen is 2. Hope it is clear. Let me give you some more examples. And this is going to be much more interesting. Come on, let us consider aluminium. Check this out. But be sure that you seriously follow the concept. Look at this. 2 aluminium atoms are combining with 3 oxygen atoms. But we always go for one aluminium atom, I mean one atom. How much is that? Half. Make it half. Make it half. You get 1.5 oxygen atoms with which one atom of aluminium is combining. But we know that we generally go for double. Double. Double to this is 3. Yes, of course. In this case, the valency of aluminium is 3. Let me give you one more. Take carbon dioxide. You know, in this, one carbon atom is combining with the 2 oxygen atoms. Right? One carbon atom is combining with 2 oxygen atoms. Of course, this is okay for us. But in this case, I mean, in case of oxygen, we have to consider double. Double. So what is the double? For 2, it is a 4. Therefore, the valency of carbon with respect to oxygen here is 4. I hope this is clear with all these examples. Of course, we'll take some more. But for now, let me write that it is not exactly equal to the number, but it is a double the number of oxygen atoms with which one atom of an element combines. Only difference is double the number of oxygen atoms. Again, of course, combining with just one atom. This is always the same, but only difference is this. Check out. If you want, I'll take some more examples. Let us go for say P4O10. This is interesting. Come on. See the calculation part. 4 phosphorus atoms are combining with 10 oxygen atoms. But as per the definition, we have to consider only one phosphorus atom combines with how many? By 4, make it by 4. 10 by 4 is 2.5. So one phosphorus atom is combining with 2.5 oxygen atoms. But we don't generally consider this as straight away. We take double. So what is double to this? Double to 2.5 is 5. So the valency of phosphorus with respect to oxygen is 5. Let me take one more. Come on, sulfur trioxide. One atom of sulfur is of course combining with 3 atoms of oxygen. Right. Of course, we need to consider only one atom. The same one atom is obviously present here. But here we need to consider double to this. What is double to 3? That is of course a 6. Now the valency of sulfur with respect to oxygen is 6. So this way we can take some more. Take Cl2O7. What is the valency of chlorine with respect to oxygen? Come on. 2 chlorine atoms are combining with 7 oxygen atoms. Then 1 chlorine combines with how many? Of course, 7/2. Right. We have to consider 1 atom of the chlorine element. Yes, we have considered that. But double to this is what we have to take. So what is double to 7/2? I mean multiplied by 2 will give you 7. So the valency of chlorine with respect to oxygen in Cl2O7 is a 7. One last. Go for XeO for xenon tetroxide. In this case, if you consider one xenon atom is combining with 4 oxygen atoms. Of course, 1 atom of xenon is what we have to consider. But when it is combining with 4 oxygen atoms, we have to consider double to that. What is double to this? 8. So the valency of xenon with respect to oxygen is 8. Got it? But why double? You know, in case of hydrogen and chlorine, we have considered equal. Whereas in case of oxygen, we are taking it a double. Because remember, in these two cases, valency is just 1. Whereas here, in this case, the valency is 2. That means hydrogen and chlorine, you know, they just form only 1 bond, whereas oxygen forms 2 bonds. With the other elements in general. So that is the reason why we are taking double. I'll show you this, of course, later, but for the time being, remember, hydrogen and chlorine generally form single bonds, whereas oxygen normally forms a double bond with the other element. 2 bonds, 2 bonds. Of course, not a double bond, maybe 2 single bonds. But 1 oxygen forms 2 bonds, whereas 1 hydrogen or 1 chlorine forms only 1 bond. Remember this, will show you how, not now, but later. So now going for yes, coming to Criss cross method. Let me just give you one interesting example. You know, based on the valencies of elements, we generally write the formulae of chemical compounds. Formulae of chemical compounds. You know, formula is a way of representing a chemical compound using symbols for the atoms present in it. I already told you that the compounds are made up of molecules. Elements are made of atoms. Compounds are made of molecules. Now the compounds are of course represented in shorthand form using the formula. Let me straight away go for the example. Would actually like to take some examples now. Let us go for the basic one. Sodium chloride. Now, every time when you write some formula or some name of a chemical compound, check for the cations and anions present in it. Now, this is the question that is asked. We know that the formula of sodium ion is Na plus. I told you just now. Similarly, the formula of chloride ion is Cl minus. Isn't it? Even this also is being discussed. So now you should know the formulae of the ions or the radicals. Of course, I have given the list of all the radicals. But now look at this. Coming to the valency. You know the valency of this. Okay, let me just take it this. Na1 plus, Cl1 minus. Before the symbol, I mean before the positive, you have to write the charge, I mean the magnitude. And remember, while writing the valency, do not consider the plus sign, the minus signs, because valency is never associated with any sign. So, you know, we call this charge. Charge 1 plus 1 minus. But when it comes to valency, only one. Remember, valency is never associated with any sign. In fact, it is represented by Roman numerals. I mean, we need to write it this way. But of course, in the common practice, we just go for the regular numbers. No problem, no problem. It has become a tradition to write that. Now, this is when the crisscross method comes into picture. Cross the valency. Criss is the name of the sign. And you are crossing the valencies. Come on, cross the valence. Na1, Cl1, Na1, Cl1. So the formula of sodium chloride can simply be written as NaCl. Hope this is clear. Let me give you one more example. One more. Of course, we'll give you many. Let us see one more to get some more clarity. The second example. Let me take my second example. Come on, even in this also, there is aluminum ion, which is the cation, and sulfate ion, which is the anion. Simple cation, compound anion. Hope that is very clear. Come on, aluminum ion is Al plus 3. Just now I told you. Coming to sulfate ion, SO4, 2 minus, isn't it? Now the charge is a 3 plus. Here the charge is 2 minus. So this is from this, of course, we will be writing the valence. Now the valency of this is 3. I told you not to consider the charges. It's a trivalent cation because the valency is 3. How about this? It's a bivalent anion. The valency is 2. Okay. Now, come on. Cross the valence. Forget about these two. Once the valencies are written. Now, come on. Al2. SO4 taken thrice. SO4 taken thrice. 3 times. You have to apply this 3 to the whole thing. Okay. So that is about aluminum sulfate. One last, I mean the one that I asked you right in the first class. Ferric ferrocyanide. Come on, the formula of ferric ion is Fe plus 3. It's a trivalent cation. Coming to the formula of ferrocyanide, FeCN, taken 6 times, 4 minus. It's a tetravalent anion. Tetra, 4, valent, valency, anion, because it has got negative charge. Come on, the valencies. In this case, it is 3. In this case, it is a 4. Yes, of course. Round up the charges. Do not consider them once the valencies are written. Yes. Yes. So the formula of a ferric ferrocyanide can be written as this. So this is the formula of ferric ferrocyanide. Fe4, FeCN6 taken thrice. Right. So this is what we have discussed all these days, right from what chemistry is to this particular topic. Okay.